so I did a video last night and I had quite an interesting morning. I thought I'd talk about it a bit. By the way, I'm a huge fan of Moomin Troll, and on my holidays I went to Finland, Helsinki, and I nearly went to Moomin Land but didn't. In fact, I got this at the Moomin Cafe, and that's the Groke, and she's chasing Moomin Troll. So in case you're wondering, I'm a fanatic for Moomin Troll. But beside that, we spent that video that I did talking about these things, button cells. And as an example of a button cell, we used a Panasonic, and it's caused a number of comments that are all the same. Now, I hate writing, so I thought I'd do a video so that whenever I get the same comment, which is probably going to be inevitable, I can just point people at the video. It is interesting that when somebody doesn't agree with you, if they won't want to agree with you, then what they usually do is call you unscientific. So you're unscientific, your methodology is crap, your results are spurious, and so on and so on. It's a bit like a religion. If you disagree with somebody, you are called an apostate, and if you disagree with somebody in the scientific world, you're unscientific. It's very funny. But the claim is that I wasn't being fair to these things. And that's not an unreasonable claim. And of course, the whole test really wasn't to be fair to these Panasonic button cells. I've no interest, really, in these Panasonic button cells. It's not meant to test the power on these little button cells. It's just not meant to do that. So when people start making comments about it and they start talking about how you should go around dealing with these things, well, it's actually a fair comment, and I thought that I would talk a little bit about that, but it also misses the point of what the video is about, because it's not to do with testing fairly these particular cells. That's not what the video is about. The video is about how does a button cell perform under those test conditions. Now, that's a different test. If I wanted to test this button cell for its energy density, I would do something different, but I didn't. I wanted a specific draw that I could measure and to see how this would perform against our version of the button cell. That was the test. If you don't appreciate that's the test, then you're probably missing the point. But when people were talking a little bit about them, they started talking about discharge rates. Now, that's actually a reasonable comment, and it's reasonable to consider those things. Now let's say that this has an overall capacity of 200 milliamp hours. It's not far off what Panasonic claim for it actually. Panasonic claim, I think it's 225 milliamp hours. Well, let's say it's 200 milliamp hours. That is the capacity of the weight of material in this device. Now, if I were to discharge that at 1C, what that means is I would discharge that over 1 hour at its capacity. So I'd find something that discharged at 200 milliamp hours for 1 hour, and that would supposedly run at 200 milliamp hours for that entire hour at that fixed voltage. That's what it actually means when you're talking about the C-rate discharge. And that's okay because it makes sense. Now, C-rate discharges are to do with the amount of material. And as everybody knows in the battery world, if you discharge something above or below the C-rate, then the material has an ability to cope with it or not. None of the batteries in the world cope with high C-rate discharge particularly well. If I were to graph that C-rate discharge, what I would do is I'd have an axis here on power and an axis here on time. I would discharge it at, say, 1C. And the shape of the curve I would expect would be a little drop off, a long line, and then off the end. And it had a certain size and a certain area of that curve which would give me the supposed power on a particular device discharged at 1C. Now that makes a lot of sense. Perfectly easy to understand. The problem comes when you discharge it at higher than 1C, so 5 times its rate, or 10 times its rate, or as Turniger want to do, I think 100 times its rate, then that long power curve moves along. You get less and less out of it the higher the C-rate discharge that you use. So if we use a C-rate discharge of 10C, we're going to get about, I guess, okay, 68% of the power. If we do it at 100C, we'll get about 6.8% of the power. They're just figures I pulled from the air, incidentally, just to give you an illustration of what I'm talking about. That curve shortens until you get that shape to it. Now, we saw that on the Panasonic, and that's reasonable. It's what you'd expect to do because it was a high C-rate discharge. Remember, this is supposed to have 225 milliamps. I discharged it around about 150 milliamps, something like that. So we're looking at about C over 2, a half C, something like that. So it would shrink the curve down. That's right, it does that. All batteries do that when you discharge them at a high C rate. Now, the converse happens. If you discharge them at a slow C rate, so you do it like C over 2, C over 5, C over 20, then that curve extends. It gets longer because you get more out of it because you're allowing it time. Now you have to remember these things are reactions, they're chemical reactions. They're the movement of ions, so it takes time. If you can give it the time for those ions to move and those reactions to occur, then you get more out of it, or you seem to get more out of it, but you have to give it time. If you do it too quickly, all those reactions can't happen quickly enough, so you can't get it all out. And you get that phenomena, when you pick these back out, you get that apparent rebound of the voltage as it catches up with itself, if you like. So if we extend that C and we do it C over 20, then that line will go much longer until it drops off. Now it's standard to do lead-acid batteries at C over 20 to give you an idea of what a lead-acid battery can deliver you. And that's because lead-acid batteries are inherently slow. What Panasonic did with this is they did it at 0.2 milliamps, giving this on their data sheet at about C over 1,000. Now, C over 1,000, to my mind, is ludicrous. Sorry, I just had a worry there that the microphone wasn't on, but it's on, so I was just checking the microphone. Oh, incidentally, on that aside, the microphone we use is a Zoom H2N, nice microphone, but you're in a lab, you're not in a recording studio, so you get noise. The microphone's really good, and I was just checking it was on. Anyway, where was I? Oh, yes. So, Panasonic used C over 1,000, which to my mind is far too gentle. That's just crazy. I can't think of anything that uses 0.2 of a milliamp hour apart from something like maybe the leakage on a diode, maybe, I don't know. So what did I do with those things? Well, I set up a circuit that has a high draw, certainly, and I stuck this battery in and had a look to see if it could cope. Lo and behold, it could, but only just. Ours coped beautifully, as you saw, and that's all that test is telling you, that in those test conditions, with that load, this can't cope and ours can. Finish! That's all it's telling you. What do I need to do next? Well, clearly, on that talk about C discharge rates, which is a very valuable comment, remember, what we need to do really is match the C rate of this to the circuit that we're going to drive. Now, if I do that, then this little device will be able to cope with that slower C rate discharge. That's very true. But then, so will our device. They're both button cells, both the same size, have roughly the same amount of material in them. Ours is just more power dense than this, but it doesn't tell you that much about the energy density. We know what the energy density is given that test, but we don't know what the real energy density is. Now, Panasonic claimed 225 milliamp hours at C over 1,000. That's the energy density for this. That's absolute nonsense. But it's still what they say. We know that ours in that test conditions has a specific energy and a specific power, which we've had a look at. Yes, we do need to do it under a lower discharge rate to see what it would be under the lower discharge rate. And if I was looking or investigating the quality of this particular device, I would do it under different discharge rates to get those curves. Sorry about the traffic. To get those curves so that I could have a look at them, and I would do the same thing with our battery. Now, of course, I've been doing that with our battery on other videos, and of course I do that endlessly. That's what I do all day. I don't just sit and drink tea out of Moomintroll mugs. I do that kind of stuff. So, sooner or later I'll do a video on it, but I have a lot to do, and the other videos I'm going to do I think are going to be more interesting. But equally, I needed, I think, to address those particular issues that people were raising. One is, don't assume something and then make your argument based on your own assumptions. I'm not investigating this, so telling me I'm not investigating this is a waste of time. I know I'm not. I'm not investigating the FWG button cell either, I know that. I'm just comparing these two things in that particular setup, and that's all you've got. And I think that's a reasonable thing. There's the test. Make what you like out of it. But don't create an argument for me that you think you can win by saying those stuff. That I think is a waste of time. And anybody who says you're unscientific, I just think that they're basically pseudo-religious types who are desperate to win an argument, and good luck with that one. Anyway, I thought you'd be interested, and I hope it's a reply to lots of the questions, and thank you very much for watching.